Let's begin. First, we must ask, what is a heat engine? Well, if you break it down, a heat engine is a device that is able to convert thermal energy into mechanical energy, and in more modern times, these engines have been largely replaced by internal combustion engines, but more modern instances of the heat engine include steam engines used in trains and such, and the turbines of nuclear reactors, where nuclear power is used to heat water to spin turbines, resulting in the production of electricity. As for how a heat engine works, a heat engine's basic function is simple. You add heat energy to a substance, usually gas, as gases expand and change volume more easily than solids or liquids. The simplest example of a heat engine is a piston with a gas inside the cylinder that is heated to expand the gas and to do work on the piston, thus turning the thermal energy of the heat source into the mechanical energy of the moving piston. More complicated heat engines have both a heat chamber and a cold sink, where the remaining thermal energy that isn't used to do work is dissipated in order to create a cyclical cycle to make the process of the heat engine continuous as you continually add more heat, thus making a heat engine. Basic functions of a heat engine are primarily reliant on the laws of thermodynamics. The first law of thermodynamics explains that the flow of energy within and without of a defined system. It says that the change in thermal energy, or delta U, of a system is equal to the heat Q and the work W of the system. Keep in mind that both Q and W can have negative values, signifying that the system is either doing work on the surroundings or it's heating its surroundings. The value that is negative will be the value that the system is doing on its surroundings. For an example, the work value on a system is negative, thus the system is doing work on the surroundings. In the case of heat engines, the system being the heat engine and the surroundings being everything else. The second law of thermodynamics, that heat flows from hot to cold or high energy to low energy spontaneously, is also important for the basic functions of heat engines. If you recall, heat engines generally have a heating element or a cold sink or cooling element. The second law makes it such that the excess heat of the heat engine spontaneously flows to the cold sink, making the heat engine function by simply heating the heat chamber, because the excess heat flows from the heat chamber to the cold sink and is dissipated there and cools the system, preparing the heat engine to do work again. The third law of thermodynamics is less useful to the process of heat engines, but is useful to know. The third law states that you cannot reach zero entropy in a system or absolute zero temperature in a system in a finite number of steps. This law is useful to know, but when applied to actual heat engines, it's impractical, as heat engines do not reach absolute zero. Other fundamental equations you need to know from the process of heat engines are the three displayed. PV equals nRT is useful as it directly relates temperature to volume and can be used to find changes in volume and or changes in pressure, which are used in calculating work or heat, as you can also use the equation to calculate changes in temperature. Keep in mind that moles, or N, is not in kilograms. It is a mass unit that not a mass unit that must be converted into moles by using the substance's molar mass, or whatever the heating element is. Making this equation an all-around useful one to know, as it combines both pressure, volume, temperature, and indirectly mass. Q equals mc delta T is useful primarily in calculating heat in or out of a system and calculating the delta U on the system. Work equals P delta V is the main equation for calculating work on a system. As heat engines work primarily at constant pressure, it's a simple and easy way to calculate work either in or out of a system. Keep in mind that a heat engine's work is almost always negative, as the engine is doing work on its surroundings. So for those of you in AP Chemistry right now, you also will note that AP Chemistry puts work equals negative P delta V, such to make that it negative. Alright. Engine efficiency is a relatively simple way of knowing how much work you're getting and for how much energy you're putting into an engine. Simply put, it's the ratio of energy in compared to the energy out. It's the energy in compared to the energy out, and can be calculated either by using temperatures or the more simple way of doing it, dividing the energy or work done by the engine by the thermal energy you put in the engine. In this manner, engines with an efficiency of less than 1 are not perfect and dissipate some energy into its surroundings where it's lost and you can't use it. Engines with an efficiency of 1 are perfect and do not lose any energy to the surroundings except for the function you have specified. So for an engine, it moves the piston in and out, stuff like that. Perfect engines are near impossible to make, as the real-world non-conservative forces like friction or air resistance or other stuff are everywhere, and they all inhibit this perfection. To give you an example, the human body is only about 30% efficient and wastes a lot of the potential chemical energy available to it. And engines with an efficiency greater than 1 do not exist because it violates the conservation of energy and saying that you get more energy out than the energy you supplied. So you can't get more energy out than you put in. Now, specifics regarding to the equation at the top of the page, you see here, it's a simple ratio of the work you get out of the engine compared to the heat you put in, and it's an absolute value because work is negative, and in an engine, because the engine is doing work on its surroundings, and you cannot have negative efficiency. For this reason, it is in the absolute value brackets. The other equation that uses temperature is a bit more complex, as the temperatures described are the temperatures of the cold sink and the heating element of the engine. The equation generally describes the difference in temperature of the heating element and the cold sink divided by the temperature of the heating element is the same ratio as the efficiency of the engine. So it's a bit more complex, but it's still relatively simple. You just got to remember that the temperatures are the temperature of the heating chamber and the temperatures of the cold chamber. You just remember that. Alright. So, the Stirling engine is a simple piston-based heat engine. The animation below shows the cycle of a Stirling engine. In the top cylinder, heat is added, causing the gas inside to expand, pushing the piston out, doing mechanical work, and expanding the lower cylinder, because it's expanding the gas in all cylinders. As the gas pushes to the lower cylinder out, it is exposed to the cold sink, causing the gas to contract, restarting the cycle. This allows the heat engine to run continuously without having to add or remove input heat and contract the working substance. This shows how the first and second law of thermodynamics can be put into action, as heat is added to the piston expands due to the PV equals nRT equation, and because of the second law of thermo, the heat flows from the hot chamber to the cold one, cooling off the gas and contracting both pistons, restarting the cycle of the engine. In the corner next, in the other corner of the slide, you'll see that it's a pressure versus volume graph of an idealized Stirling engine. From steps 3 to 4, the gas expands isothermally, doing mechanical work as it's heated. From 1 to 2, the gas is recompressed as it vents remaining heat into the cold sink. So this is the ideal Stirling cycle of a pressure versus volume graph. Alright, review question time. You have a heat engine filled with 24.0246 moles of argon gas that is being heated to pull a 200 kilogram man up a tree. The temperature of the cold sink being at 305 degrees Kelvin and the heat reservoir of 345 degrees Kelvin at a constant pressure of 1 atmosphere. Knowing that the specific heat of argon is 520.3 joules per kilogram degree Kelvin, and its molar mass being 40 grams per mole, what is the efficiency of the engine, what is the change in internal energy, and how far up the tree will the heat engine pull the man? Alright, and once you've finished answering that question, here are the answers. Yay! So, hope you had fun listening. We'll see you tomorrow with more videos.